Yes. Okay, we are close to 50 people, so I think we can start. So welcome everybody to the talk. I'm glad to see so many people here, and I'm happy to introduce Blaž Gasparini, who will present today his opinion paper in ACP. And let's say I asked Blaž to give me some information to introduce him, but it was very short. But I remember that you spent your PhD time in Zurich. I think we met first during that time, and in the group of Ulrike Lohmann. And as a postdoc, you moved to University of Washington for something like 3 years or so. And now from there, he moved to University of Vienna, where he works now. And he worked on extratropical cirrus modeling, and then shifted more to the tropical cirrus, looking at climate impacts and interaction with radiation. And so the tropical cirrus is the topic today of his talk. And please, Blaž, go ahead. We are really interested to hear what you are saying.
Great. Yeah. Well, thanks for giving me the chance to present here. And yes, indeed, this talk is partially related to this opinion piece, but that one is relatively long. So thanks God I'm not talking about everything, because that would take more than an hour, I guess. So I'll focus here more about two of the aspects. And one is the representation of tropical cirrus, and the other one is the cloud feedbacks, or the responses of tropical cirrus to global warming. Well, mainly anvils, because we don't know much about those thin clouds yet. So, all right. Well, if I start with something very general, if we zoom out and look from the geostationary perspective down at the Earth, at the tropics, we see that this part of the Earth is very cloudy, and that there's a lot of things moving, a lot of clouds moving, different cloud systems. And now if we go down into the near Earth orbit, so now we are at the International Space Station, we look down in that area and we do see that there's a multiple different cloud types present at the same time, but many of these cloud types originate from some sort of deep convective sources. You see that we have some deep convective clouds in the beginning of their development, some rather aged ones. We do have some of these detrained clouds that start in deep convective cores, so anvil clouds that I'll talk a lot about. And also we do see here quite nicely, and often we don't see that as nice because they're very thin, but we do see that these thin cirrus are practically always up there present. So the thin cirrus in the TTL, in the tropical tropopause layer. Okay, here we do see also quite some stratocumulus below. It's a morning picture, morning snapshot, so maybe those are a little bit over-represented compared to what you would on average see in that region. And there's one kind of very important or dominant cloud type that is maybe a little bit missing here from that picture, and that is the fact that we have often in that region clouds clustered in these big thunderstorm clusters or mesoscale convective systems, and I think many of you would know for that. Well, they would have at least one, but more commonly more deep convective cores, and they would live for quite a long time, and they would really be the source of most of this upper tropospheric ice in the tropics. And we do see that these anvil clouds, shields, can really extend to quite large areas. So often, more than 100 times 100 kilometers, if not even more. And I believe most people that work on that topic and think about anvil clouds and convection would look at that from the precipitation perspective, and that is indeed very important. We know that anvils or some sort of deep convective mesoscale clusters would really bring most precipitation, most rain in the tropics, no doubt about that. But I really want to focus more on the climate aspects and on the energy balance, because these type of clouds are basically some sort of cloud which is detrained from deep convection, so some sort of a tropical high cloud or tropical cirrus. We know it's the most frequent cloud type in the deep tropics, but not only that, also actually contributes most to the total cloud radiative effects in that region. I mean, and it's really this type of envelopes which are most radiatively important simply because, well, they cover this large portions of the tropics compared to the rather more isolated or smaller deep convective cores. So, and now if we look at this picture for the cloud radiative effects on the albedo or reflectivity side on the left, so shortwave and longwave greenhouse effect on the right, we see that actually both of these effects are quite big, if not the biggest in this region, in the tropical warm pool area, but a bit, I would say, everywhere near the intertropical convergence zone in the areas where there's a lot of deep convection in tropics. So that's why you can imagine that if there is something that changes just a little bit in the structure of this cloud, you can have quite a big impact on the radiative balance. And you can think, there could be some aerosol cloud interactions or just some responses to, for example, global warming. And that's one motivation, why I think it's very important to look into clouds like that. So, and another, of course, the reason why we want to look at that is because there's so many different processes combined and influence these type of clouds. And not all of those are well understood. Just in short, so anvils or the altitude of anvils where this detrainment of ice happens is really controlled by the large-scale thermodynamic processes or even radiative processes, most notably the clear sky radiative cooling, which really determines you where you're sort of on the clear sky areas losing air due to subsidence, and that has to be filled in by the detrainment of air from deep convection. So then on the other side, we have convection itself, and somewhere in between, we have this multitude of processes from microphysics to turbulence to radiative processes, which will feedback, interact between themselves, but also will have some implications for the large scale climate, but also the mesoscale, so multiple scale problem. And above those anvil clouds, in the tropics, we have super frequently some sort of a very thin cloud in the tropical tropopause layer, so TTL cirrus. And now these are a bit different because they're generally not really formed by direct detrainment of ice, but they would form by ice nucleation. And actually, we don't know too much about their formation. There's still a lot of discussions whether more important homogeneous or the heterogeneous ice nucleation up there. But definitely that is important, and particularly also important the fact that they would form or be triggered by gravity waves. I mean, also sort of helped by the large scale conditions, the large scale ascent in that region, but ultimately it's the gravity waves which actually originate in deep convective sources in the tropics that would really generate those clouds. I don't really focus too much on those today because, again, the talk would become a bit too long if I would try to get everything here. All right, so I will, as anticipated, talk a little bit about how we are dealing with, or where we are with modeling of those cirrus, and then talking about the responses to global warming and present a few ways with which we can advance in this field. So now, if we come back to this picture that I showed you before, you can imagine, I mean, this is maybe 200 times 200 kilometers or so represented by standard climate models in terms of 1 or 2 grid boxes. You can be smart, you can do some smart parameterizations, of course. You can do it sort of right, but it's really hard still to get really all this complexity in this 1 or 2 columns of a standard climate model, no matter how good you are. So, and it's not surprising that therefore many climate models wouldn't get this type of clouds right. And I'm not showing now examples of that, but can believe me that. And on the other hand, these days it's becoming super fancy and popular to look at snapshots like that. I mean, this is this iconic, I would say at this point, figure from the Diamond high resolution global storm resolving model paper, where we see a snapshot of 8 global storm resolving models and one snapshot from the satellite. And when you look at it so from the distance, it's really hard to say which is now the satellite and what are the models. So it is true that these models from distance, at least, when you look at snapshots, they look beautifully. They do represent all this variability and clouds, at least in this sort of rough sort of view from, again, distance. Let's say we're looking from the geostationary orbit down. Indeed, this type of models will be more realistic to some extent, because we will be moving from the CIMIP type climate models, 100-kilometer scale resolutions, which will resolve the large scale, planetary scale stuff, synoptic scale, weather disturbances, to resolution of 1 kilometer, maybe even higher than that if we think about 5 years from now, maybe. And indeed, we will start resolving some of the very important processes there, particularly deep convection, which is the main source of ice in the tropics. So we would expect really that we do gain something when we switch to high resolution. And no matter whether this is, thinking about these global storm resolving models or just having rather limited domain cloud resolving models, or even something higher than that, which probably is not feasible to be run at this point at the global scale. So yeah, in the beginning of this talk, because of that, I'll dig into a little bit, dig into this global storm resolving models and go beyond this sort of nice, beautiful snapshot perspective and focus on cloud ice. So now here I revealed which of these figures or spheres that I showed you before is a satellite. So it's this one on the top right. And here I'm showing on top of that the outcomes from the 4 global storm resolving models, all at resolutions of about 3 to 5 kilometers, horizontal resolution, maybe about 200, 300 meters vertical resolution at Cirrus levels. And I start by looking at, let's say, squeezing the ice in the atmosphere in one layer. So looking at the frozen water path or ice water path, whatever you want to call it. So it's not only ice, but it's also snow and graupel and whatever. And here showing first the perspective from the active sensors, so from the DARDAR observational or remote sensing data set, where you do see that first, these are the very thick clouds. Category 1 would be deep convective clouds and maybe some very fresh envelopes. They do occur, but not that super frequently in that region. And I'm talking about really the warm pool region, the region where convection is really frequent. And on the other hand, then we see that we have this areas of intermediate to low frozen or ice water path, which are very frequent. And these areas, or this sort of peak of the distribution, is really related to clouds of intermediate optical depth, or even optical depth of 1. You could say this is a rather thin cloud. And those are the envelope clouds, or aged envelope clouds. And finally, then maybe thin cirrus, which, can come from direct detrainment of ice, or it can come also from in situ sources of ice, so sort of ice nucleation and gravity waves. And now, showing the same from these models, you see, first that those models have large intermodal diversity. So, some people maybe hope now we increase the resolution, we resolve convection, and this uncertainty will become smaller. Doesn't seem to be the case. Secondly, if I can say something, shared between these models, we do see that, at least in that region that we're looking at, all these models share this bias of not having enough of this very thick clouds or deep convective clouds. But other than that, I think I can just conclude that they're very different between each other, and that, they, or some of them at least, may be quite far off the observations. So we do have large diversity, and just increasing the resolution will not solve all of your problems. And I do believe if we added a few climate models here, show them in the same perspective, we may not be very different from the observations, or more different compared to this global cloud resolving models. So now this is the ice water perspective. If you look in the atmosphere, and this is now on the left, a rather old picture from the old generation of CIMIP models, where you do see that there is a large spread in ice water content within the atmosphere compared to the black line, to the observations. Maybe I should say that observations, of course, have also a large uncertainty, to be fair. But anyway, we now switch to the global storm resolving models. We do see that this uncertainty or spread between the models doesn't really decrease, at least from the current generation of global storm resolving models. And those are 5 of them plotted together with the observations. So I would say the spread is at least of similar magnitude compared to GCM. So that may not be such a good message for us working on ice phase. At least not, will not get that right immediately. But then on the other hand, if we look now again at this sort of scales of atmospheric processes, now we're going from 100 kilometer to a kilometer scale, and because of that, we can get rid of some of the model parameterizations, which are really source of uncertainty or unphysicality in models, so to say. And what happens actually while doing so is we are really transferring some of the uncertainty that was hidden in these parameterizations into the remaining parameterizations which are out there. So turbulence, radiation, and microphysics. So we're sort of empowering those. And this is an example of what happens if you look at just one of these global storm resolving models. So this is SAM. So one model, but coupled to 4 microphysical schemes. And just from this snapshot perspective of, again, frozen water path, you do see that the weather systems are represented quite differently by these different microphysical schemes. So some will have more extensive clouds, some thicker clouds, and so on and so forth. So I would say that really now we are giving even more power to the microphysics, and that's not important just for the microphysics itself, but particularly because this will also lead to substantial biases, or will substantially modulate the radiative fluxes. So you will see that here in tropical average, we can go when we switch microphysical schemes from -12 bias to -6, so quite 6 watts per meter square difference, which is quite big, or on the long wave side, even bigger differences. So yeah, I think we're really, by switching to high resolution, empowering some of these processes which are left there. And I point out here microphysics. I know something about it. I guess we could probably also have a story about turbulence, I imagine. So, okay, well, microphysics was always powerful, but now it seems to be maybe even more powerful and important. So I think we should have a close look at that and look at these processes and how actually these big models are simulating those processes. And I'm here talking about, in particular, one model about the SAM cloud resolving model, actually not run in the global regime, but in some sort of a channel setup, which represents what's going on in the tropical Pacific well. But I would say that what we get from our setup, it's probably generalizable also to the global or tropical perspective. So that wouldn't be very different. All right, so I will talk about this model. And if you look at snapshots from this model, which is coupled to P3 microphysics, they look fantastic. I mean, you see active dip convection, you do see this nice mesoscale convective system precipitating on one side, and then the anvils, and then you even form TTL Cirrus. Well, at least this is the final setup where we fix microphysics, and we could form really this TTL Cirrus. But anyway, so now I want to show you a little bit more quantitative perspective focused on the ice cloud properties, not only on these nice snapshots. We know that these models can do that. And the goal here is to improve those ice cloud properties and do so by using, quick fixes to the models, not going anything very complicated. So for that, I like to look at this perspective, this two-dimensional phase space, which may be a little bit different from what you're used to see. So we have ice crystal number on the y-axis and mean mass radius of, well, the ice on the x-axis, which is just a division basically between ice crystal number and or mass and ice crystal number. And those are the tropical field campaigns, 3 or so tropical field campaigns measurements. So it's a two-dimensional PDF. And you do see that, yeah, well, we get a lot of stuff at about 100 per liter or 0.1 per cubic centimeter concentrations and very small ice crystals. And we do have still quite a lot of high ice crystal number measurements in that region. And of course, the question is, can the model do it? And the answer is, I think, at this point, very clear. Well, it's a no. At least that's the model that you get out of the box, or this cloud resolving model with the out-of-the-box P3 microphysics. And we clearly do see some biases, which look weird. We clearly do see that there's no high ice crystal number points. So that's an easy one. Well, then you look at the code and you see that there's some artificiality in the code, so that you do have some limits. For example, the upper ice crystal number limit, you remove that, and then, well, the situation looks different. I wouldn't argue necessarily this is better. It's more physical. It's different. So that was good. We're now more, able to simulate stuff in a more physical way, but we're still very far off the aircraft measurements. So there's more. And what I notice here is that, and what is actually very common in this, particularly in these global storm resolving models, they have very simple way of representing microphysical processes, particularly when you look at Cirrus processes below homogeneous freezing of water. Often you would have these freezing parameterizations, which would just extend freezing parameterization, which was meant to work in mixed phase, to Cirrus conditions. So that's not good. And that's what was done in this specific model, in this specific microphysical package. And yeah, well, for those that know, so basically we had deposition freezing from the mixed phase, which was just extended to nucleate ice everywhere at cold temperatures. And I made a quick fix, which is still imperfect. And for people that care a lot about microphysics, there's better solutions to that. But that was a easy, quick fix that didn't make the model more computationally expensive, and that is still representing now this process of homogeneous and heterogeneous nucleation at Cirrus conditions that we see here now. So we did that, we modified it, and now we do get this two-dimensional PDF, which does start to resemble a little bit the aircraft measurements. I mean, we did boost a little bit the ice crystal number. We're better. I mean, you may say, well, we're still far away from the observations. And yeah, I agree. But to be fair, part of those biases are due to the wrong input to microphysics. So even at kilometer scales, and we are having here horizontal resolution of kilometer and vertical of 200 meters, we're not really resolving all the updrafts that are needed for cloud formation. So I'll actually look more into that in a moment. But then also I would say that the aircraft measurements are in general not really sampling that much in the active deep convective cores, and we may be undersampling that region. So we do see here quite a lot of particles being simulated by the models, but not in the measurements. And yeah, maybe we shouldn't focus too much on that bias there, because it may not be super real. All right, so now we saw that we were at this SAM model at a kilometer scale, and my question here to all of you is, well, what do you think actually, according to you, if you can guess, would be the right resolution? And now I'm talking just about horizontal resolution to really resolve the relevant motion for particular anvil cloud or tropical cirrus in general formation. Do we need to go, are we good at 1 kilometer? Maybe not. Are we good at 100 meters? Do we need to go to a meter? So now, hopefully, this survey will start, and hopefully you see it, and you see the QR code. So hopefully you have the phone there, and you can scan it and then give me or give us some answer. So I put a few options, and I'm curious what sort of is the general feeling in this group of people. I've never done this poll, or at least not for this question, so I'm actually quite curious. So I'll wait a little bit to get some representative number of responses. Nice. I think the participation rate is really high. I think we're sort of starting to settle on an answer. Oh, no, we're not. Okay, so we're somewhere. It feels like we're not super certain, but it seems like we have to go at least to a 300 or below 300 meter resolution, maybe even to a resolution of yeah, somewhere around 100 meters or even below 100 meters. So we're there. I mean, certainly not about a kilometer or more, certainly not more than 300 meters. So it seems like even 30 to 100 meters. Good. Nice. So let's see what some of my recent results say. So this is actually quite a depressing outlook, actually, what you have. So basically, if we have to go to 50-meter horizontal resolution, that's tough. All right. So now this is my more recent work done particularly together with Rachel, who produced these plots. What I'm showing here is the standard deviation of the updraft PDF. So that is sort of one quantity which tells you, something important about the whole distribution of the updrafts. So I think it's nicer to digest than looking at PDFs. And yeah, we have it being by altitude, and we have the two field campaigns from the tropical Western Pacific that sampled, and we do have this model now ran at a resolution of 4 kilometers. And maybe now this is a positive surprise, what I'm showing here. So even when we are 4 kilometers, when we are near active convection, the black lines are totally fine, are totally in line with the observations. And, we go then to 1 kilometer, we go to 250 meters. We are always somewhere very close to the observations. Observations were, of course, also resampled. That's why they changed a little bit when we changed resolution. So seems like the global storm resolving models may be fine for simulating processes near active deep convection. That makes sort of sense, but still, it's a nice positive message, I think, after telling you some more negative stuff before. Yeah, okay, so that's the all together. And now what is now more difficult to get to simulate in the models is, however, what happens far from deep convection. So here you see first that this updraft PDF is more narrow, or this sigma values are smaller, but you do see also that even when we go to 250-meter horizontal resolution, we're not quite there, or maybe with 250-meter, we start getting there, I would say. So there's some hope with 250 meters, but not with a kilometer. Now, maybe looking at it with a little bit different perspective. So it's the power spectrum. So how much variance will each of this wavelength bring? And here we clearly see, yeah, we're very far at 4 kilometers at 1 kilometer. So this is looking at the whole domain. I'm not distinguishing the convective and non-convective parts. But then at 250 meters, I guess I would say we get it. And okay, don't focus on this part. This is the large scale. We're not getting the large scale because of our model setup, but we do seem to be there, and that's nice to see, and a very nice way to visualize that, I would say. And finally, if we put on top of that the global storm resolving models results, we do see that, well, they are still kind of far. Not surprising, they're at sort of these resolutions. Maybe there's one which is doing something odd. That's sort of right, but for wrong reasons. You can ask Rachel for more information. There's a really nice paper, Atlas et al. 2023, if you're interested. So seems like at 250 meters, we are somewhere, and there's more evidence that at that sort of scales, we get first the convective updrafts right. That's sort of idealized work, but there's even more sort of realistic type of work showing the same. And even more interesting or positive, I would say, when we get to this 100-meter horizontal scales, we start to converge both in terms of cloud fraction and cloud macroscopic properties, but then also the process rate, so the sources and sinks of ice. And that's actually even more interesting. I'm not really sure why that happens at that point, but it does happen, and I'm not sure if that's really generalizable to all models. In that specific model, it does, even with more than one microphysical scheme. And this is, again, a SAM cloud resolving model. So it seems like when we get to this 250 or 100-meter scale, we may be getting something right. And while this is, for now, still prohibitively expensive, for larger domain simulations, of course, we have the Japanese who are about 10 years ahead of everyone, and they already start to play with these resolutions at the global scale. So, I mean, yeah, we're not there yet, but I want really to make a shout out to that group, as I don't think I cited it before. So there is potentially hope. So yeah, I mean, really getting to these 100-meter resolutions might be the right way to go, and another right way or way to go here from the modeling perspective is really like start digging into the microphysics. If you already get this high resolution model, make sure that the microphysics is sort of right. That's what I would conclude here from this part of my talk, or most of my talk. Good. So now switching gears a little bit, and this final part, the second part, will be a little bit shorter, but I think it's also very important because so much exciting work is coming up right now. And what I'm showing here about the responses of Cirrus in warmer climate, actually, we didn't really write in the opinion because all of the papers I'm talking about are just still in review mainly. So anyway, why am I talking about that? Well, because these clouds, or the responses of these clouds to global warming, are really uncertain, and actually these days even more uncertain than feedbacks due to low clouds, which were traditionally the largest source of uncertainty with cloud feedbacks. And that means really if we constrain this uncertainty, we can really constrain the climate sensitivity and the temperature increase due to doubling of CO2 by quite a little bit. So that is the general motivation, and you see particularly this tropical annual cloud area feedback was shown as quite important, quite big, quite uncertain, and quite negative, kind of controversial value there. So when we talk about the known annual cloud feedbacks or tropical cirrus feedbacks, but here really mainly talking about annuals, nobody really looked at this TTL cirrus in detail. Well, they're kind of thin, but still. So we have two processes. So one is in a warmer climate, envelopes will stay more or less constant temperature. So with the tropopause expanding or troposphere expanding, they will have to shift higher up. Fixed envelope temperature hypothesis, not really talking about that here, but that's how we call it. And the other semi-robust feedback is the fact that the cloud area will decrease in a warmer climate, and that's called the so-called stability iris mechanism. And if we now look at this stability iris mechanism, because it's a little bit less known, we do see that, yes, it appears in many of the models. Might be more complicated when you look in details, but in most models you would get it. So clouds in a warmer world shift higher up and shrink in the tropics on average. But even when we look at interannual variability, so just taking the observations and making some linear regression, we do see when it's warmer, we have less envelopes up there. It's quite clear, quite a few papers there. But the question is, okay, does this matter, right? I mean, clouds, a bit more cloud or less cloud, who cares? But does this matter for radiation? It's a real question here. And here, well, the short and long wave effects of envelopes are very big, but when you sum those up, they're more or less neutral. So, that means that if the net radiative effect is close to zero, means that, well, this change in extent of envelopes will not lead to any feedback of huge radiative importance, unless this feedback would be very big and unrealistically big. So that's one part of the story. So that's why I don't believe this area feedback should be very negative or very positive. But then what about other changes in clouds? I mean, there could be other stuff going on. So, you know, cloud thickness or cloud optical depth or opacity, whatever you want to call it. So I want to give you a few or mention it and give a perspective based on two papers that are just published or getting through on that. Before going into that, just quickly, so since the next few slides will show this type of binned perspective, just a quick intro into that. So here we're binning all the points in the tropical Pacific based on how much water, ice water content they have. And of course, those points with the most ice water content will be related to deep convection, deep convective cores. And then when you go to a lower ice amount, you'll have thick envelopes, thin envelopes, and thin cirrus. I think that's a great way to look at this type of clouds. You really see sort of a envelope and the evolution of envelope, I would say. And now let's just zoom into this part of the clouds. And let's again, you know, look at the squeeze perspective, the ice water path perspective. And to start with, we look at the interannual variability again. So no climate projection, but just looking what happened in the observations and regressing it based on the changes in tropical mean surface temperature. And we do see here that based on the cloud radar observations, if it's warmer, we get less of this thick or intermediate thick or just standard envelope clouds, but maybe a little bit more of very thick clouds, which are related to very strong convection. That's interesting. And even more interesting, the same people, they did the study with the global storm resolving model, global warming study, 1 year, 4-kilometer global resolution, and they got basically the same answer or the same result. So that's kind of intriguing, but it does sort of make sense physically if you think about what should happen with global warming, with most extreme updrafts and convection getting stronger and maybe a little bit less of envelopes. So that is very intriguing, I would say. But again, what does this mean for radiation? Because we do have this short wave and long wave component. So what does this mean now? Will this make the whole feedback enhance or dampen global warming? Okay, so now coming back to this observed PDF of ice water path, just showing what clouds are most frequent. And I showed already in the very beginning one of these, but here showing it in a little bit different perspective. also showing which part of this distribution of these clouds is leading to climate cooling effect and which to climate warming effect, present day climate, of course. So you see that actually most frequent clouds are those of that will have a small warming impact on climate. Yeah, so those are the most frequent ones, sorry. And my point here is that even if we just change this distribution by a little bit in either of the directions, we would potentially have quite a big climate impact. And now the Boileau et al. Study that I highlighted looked at this region. And they had this sort of cloud thickening for the thickest of the clouds and cloud thinning for those clouds. And it's kind of hard to say what's really going on there in sort of net. But I would extrapolate that since those clouds are a little bit more frequent, we may get some sort of thinning of the cloud and maybe a little bit more of a warming impact from these changes in this type of clouds. But beware, those very frequent clouds were not really considered in this study. Now, it's time to slowly wrap up, but there was also another study that looked at this and analyzed the whole PDF of these clouds from idealized modeling, and without going into their method and results too much, they came to the conclusion that there is a positive so-called opacity, so opacity because they consider both the long wave and the short wave part of that cloud feedback. But it's not very big, and the uncertainties are quite large. So, and of course, yeah, just this is one study, and it's quite idealized. So things could be still a bit different in the real world. So based on this 2 or 3 studies that I mentioned before, I think what we can really exclude is that this envelope cloud area maybe together with the opacity feedback is very negative. So I think we should rather move from being very negative to being slightly positive, and that will, at least based on this Sokol and Harpan study, substantially increase the climate sensitivity. So really envelopes and thinking about this feedback of envelopes can have quite a big power in modifying climate sensitivity. And if I really wrap up here, we do know what should happen in a warmer world with the large scales, large scale circulation thermodynamics. We do know to some extent what should happen with the convection, with the sources of envelopes, but the biggest unknowns are here in between. And really, this is where microphysical processes together with turbulence and radiation come into play. So I think it's really the area of cloud and cloud evolution, which we should really focus a lot on. And yeah, I think it's exciting to be working on that today. So uncertainties are huge, and think about what can happen with the ice phase and whether this cloud will get more thick or thin in a warmer world, if you think about Cirrus feedbacks, I would say. All right, so now what do I think we should be doing to get some quicker progress? I mean, I said a few things which weren't that positive about these big simulations, global storm resolving simulations, but on the other hand, if you're really interested about processes, I think it's still good to go and move to a model which can resolve a lot or more of these processes directly. That increases your process understanding. And then on the other hand, it's just like, it's beautiful to look at these snapshots, even though they might not be.
It seems that, Blanche, we can't hear you.
Okay, interesting.
You are back. Yeah. Okay.
So am I sharing? Do you see? No, I start.
No,
okay.
The screen is not shared.
If it could only wait for 1 more minute, then it would be over.
Yeah.
Let me.
Sorry about that.
I guess it was a problem on my side, I imagine, because it was on the only element of my presentation, which is more than 200 megabytes big. So anyway, I was here. I don't know where it stopped, but I assume somewhere here. So with this high resolution point, and the not only thinking about what can be improved and what cannot be improved, but also just thinking about communication and making beautiful videos. I think that's important to attract more people work on that. So that's one way forward, in my opinion. But then, as I showed, well, actually, these global storm resolving models don't really have state-of-the-art way of representing clouds, particularly not high clouds. So we may just want to fix that. It's not a very difficult task. I mean, not a very sexy task, to be fair, but someone should go do it. And also, I would say we need, well, to show a bit more clearly that now, well, microphysics is powerful. So I'm still searching for a citation for that. Maybe we should go and write a paper on that, or someone has to do it. And finally, I think I get very bored personally by seeing global averages. We should go beyond that. I mean, today we should focus on the process understanding, on the evolution, sources and sinks. So a way to do that is by, well, using trajectories. Maybe it's a bit of a messy way to do that. The other way from the modeling side, which is maybe a little bit less messy, is to use some sort of tracers, which help you with the evolution aspects. But also, of course, you should somehow connect to the observations, either in situ or satellite retrievals when you're doing that. And my connection is unstable again, but that is good because this is my summary. And I think my main message that I didn't mention here yet explicitly is that because of all what I mentioned before, I believe the Cirrus microphysical processes, at least in the context of tropical Cirrus, whether these are ENVOS or TTL Cirrus, are very relevant and probably are even more relevant today than 10 years ago. So it's time to get to work and try to constrain those processes better. Thanks.